this stays. It's just 1. The limit of 1 is 1. 2 over x goes to 0 when x approaches infinity, not when x approaches 3. When x approaches 3, this goes to 2 over 3. When x approaches 3, this goes to 3 over 9. When x approaches infinity, 2 over infinity approaches 0. When x approaches infinity, 3 over infinity squared approaches 0. When x approaches infinity, 5 over a huge is 0. So then, what is the actual limit? Look at all this and say the number is
1 over 3.
That's it. Because these are gone. When I apply the limit operator, these 3 are gone, and the only remainder constant is 1/3. So then, we found the case in which we get infinity over infinity. It's an indeterminate case, meaning no clue, have no idea, and it turns out to be 1/3. And if you remember from last time, where are my notes? We had a graph that we looked at. And we said, when x approaches infinity, if the function values get closer and closer, closer and closer to 1/3, what does y equal 1/3 mean? Is A as x approaches infinity, function values get closer and closer, closer and closer to 1/3. What does that mean? That y equals 1/3 is A.
Horizontal.
Excellent. Y equals 1/3 is a horizontal asymptote. Any questions so far, please? Yes, these limits are very interesting. Okay, let's work on one more. 41. When you work on these problems in Pearson, I'm sure you're going to come up with other examples. So we have limit as x approaches 5, the square root of x squared. So that's not to say that if you think that we need to work on another problem of any kind, you can always stop me, and I encourage you to do that. Okay, so this is the limit of a... Go ahead. Say it again.
Still relation of 1.2?
We are still in 1.2, yes. A lot of work in 1.2.
All right, sounds good.
Yes. So let's see, because this is not a linear expression, we have, regardless, we have to write that x squared minus 16 is greater than or equal to 0. But let's just plug it in. Please plug it in and let's determine the preliminary assessment. Can anyone give us the preliminary assessment?
Is that 5?
Yes.
Approaches 5?
Yes. Can anyone give us an answer?
3.
Yes. So 25 squared, 5 squared is 25. 25 minus 16 is 9. So the square root of 9 is 3. So it happened that 5 is in the domain of this expression, of this function, right? Makes the expression greater than or equal to 0. So that's why we straightforwardly got 5. Okay. There is something that I'd like to continue with, and again, you can stop me anytime, please. Something called continuity. Continuity. So a function is continuous if I can graph it like this. I graph the entire function without lifting marker off the paper. But here's what other situations are, right? So this is one situation, and we had this last time at the very end. It has a jump. This function is continuous. This function has a jump. Jump discontinuity. Discontinuity. This is N-U-I-T-Y. So this is a jump discontinuity. There is another type of discontinuity. This one. And here's the function. This function is not continuous. It's discontinuous. What type of discontinuity? This is called infinite discontinuity. And there is another one. It has a hole. But we call this a removable discontinuity. So a function is continuous if I can graph it without raising my marker or pencil off the paper. This one I cannot, this one I cannot, this one I cannot. So these three situations are referred to cases of discontinuity for a function. Okay. Now I would like us to, I'm going to share my screen and just look at a few graphs right here. So is this function continuous everywhere from negative infinity to infinity? You will say no. And I will ask you, what type of discontinuity is it? And you will say, is anyone with me?
Is it infinite?
Perfect. Is this function continuous on all its domain?
Yes.
Excellent. Excellent. Is this function continuous on all its domain?
No.
No.
What type of discontinuity?
No.
Jump. Perfect.
Continue.
Excellent. What about 50? Is 50 continuous everywhere?
No.
No.
Yes. Oh.
Right here.
Removable.
Removable. Awesome. Excellent. Good. Now, one more item here. Continuity at a point. Very important definition. Very, very important definition. So here's a function. Is this function continuous? Yes. At any point I pick, doesn't matter, on the graph. So let's say I pick this point. What does continuity at the point mean? It means that the limit from the left, the limit from the right, equals the function value at that point. That's the definition of continuity at the point. So limit as x approaches a from the function, from the left, must equal the limit from the function, of course, when x approaches a from the right, must equal f of a. It doesn't mean that the limit equals the function in general. No. If the function is continuous at a point, the limit from the left must equal the limit from the right and must equal the function value at that point. And this is not what happened on the last graph we looked at. It did not. The limit from the left was 1. The limit from the right is 0. Furthermore, the function is not even defined at 3. That's why this is discontinuous at 3. So a function is continuous at a point only if 3 things happen. The limit from the left equals the limit from the right and also equals the function value at that point. Okay. Good. So I would like us to look at an example. Oh, I'm not sharing. Where are you guys? Okay. So I would like us to look at any situation in which we're asked, is this function continuous at such and such and such? So first we can also look at this graph. So they're giving us the function, and they're asking us, they gave us the piecewise defined function, they already give us the graph. If I ask you to find the limit of c of x, so can I move this? Very nice, it just disappeared on me. Okay. Okay, so let's go through these. The limit as from the function as x approaches 2 from the right. So here's 2. What will you say the limit is 2 from the right?
1.
1, excellent. 2 from the left,
-1.
excellent. Is the limit from the left and the right, the either side, does it exist?
No.
No, because the limit from the left is -1 and the limit from the right is 1. Is this function continuous at 2?
No.
No. What is c of 2? Careful. Now we're asking about, or I'm asking the function value at 2. And you cannot give 2 values, and it cannot be ambiguous. It has to be exact.
1.
Exactly, right here, where the full point is. The full point is here, so I have to read 1. Is c continuous x equals 2? You already told me not. What type of discontinuity is there?
Jump.
Jump, excellent. Final question. Is c continuous at x equals 1.95? So 1.95 is here, so I'm talking about this point, right here where the mouse is. The cursor. Is this function continuous at this point where I have the cursor? As long as the limit from the left equals the limit from the right, and it equals the function value at that point, the answer is yes.
So no?
No.
Okay, so well, let me do this. So here's the graph. 1, 2. Here is the point 1.95. I couldn't hear you.
Yes, both of them equal 2 at that point, from the left and the right.
You mean
they're both
-1. The limit from the left is -1. The limit from the right is -1. The function value is -1.
2. Okay.
So yes, the answer is yes. The only discontinuity for this function is at 2. Everywhere else, the function is continuous. Everywhere else. Except at x equals 2. At x equals 2 is discontinuous. Jump. But the function is continuous everywhere else. Is this clear? Yes? Understood? Anyone? Yes?
Yes,
No?
ma'am. No.
Perfect. Okay. So do we still need to practice this, or are we okay with this? So let's look at 65, and then we can continue. So in 65, and which page am I on? I think I'm on 7, yes. Okay. 65, we have f of x equals x plus 2 for x less than or equal to 3, and 2x minus 5 for x greater than 3. They're asking us about continuity at x equals 3. Why or why not? Okay, perfect. So continuity at x equals 3, all I have to determine is the limit as x approaches 3 from the left, the limit as x approaches 3 from the right, and the function value at 3. If these three, 1, 2, 3, if they are equal, do I say it's continuous at x equals 3 or not?
Yes, if they're equal.
Yes, if they are all equal. Now, step by step, what am I applying the limit to? as x approaches 3 from the left. Which one? Is it this or is it this? It cannot be both, and I have to choose the exact one.
Give me the bottom one. Or, sorry, the top one.
Excellent.
Because it's less than 3.
Exactly. I know it's redundant, but what should I put here then?
2x minus 5.
Very good. And now forget about this for a moment. Where do I plug in f? Where do I plug in 3 in the function? And how much is this?
X.
Put it into x.
Good. And which one? Not in both. I have to choose the exact one in which I plug it in.
X plus 2.
Yes. So what do I get?
5.
That's it. So now, back. What is this limit equal to? Simple, because they are polynomials. I know how to find limits of a polynomial. So what is this limit?
5.
That's it. What is this limit?
1.
Yes, so 6 minus 5. Since this does not equal this, then does not equal this, what do we conclude about continuity at 3?
It's discontinuous.
Since the left does not equal the right, and it does not equal the function value at that point, what do we say about continuity at 3?
Does not exist.
We only have to say not continuous. Jump. The limit from the left is 5, the limit from the right is 1. So something like this. So this is full point because it's 5. So this approaches 5, this side approaches 1, and the function value is at 5. So this is not continuous at 3, and it's a jump discontinuity. Is this clear? Is this clear? Okay. The next section, 1.3, was already discussed. And I would only we only need to look at the average rate of change. So page 134. I don't have anything to teach you in 135. Oh, on this page. And in this section, there is nothing. So, because this was discussed already, I will refresh your memory. Average rate of change, this is 1.3. Okay, so let's choose any function, any problem. We're asked here to find the average rate of change of the given function between 1 and 5, between 0 and 6, between -4 and 0, and so on and so forth. Please choose any function. And let's find the average rate of change.
We do 20.
Which one?
20.
20, very good. So let's look at 20. So s of x equals 1 over 10 x squared plus 1/2 x between x1 equals 4 and x2 equals 7. Perfect. So if you remember, some time ago, I don't even remember, 2 weeks ago, we talked about the average rate of change, which is the average rate between 2 points, right? So we have the average rate equals f of x2 minus f of x1 is the slope of the line over x2 minus x1. I have x2 minus x1. I have 7 minus 4. How do I determine these? Oh, 7. With a graphing calculator, let me share my screen. I put the function in here in y equals. We did this before. And the function is 0.1 x squared and then plus 0.5 x. I plug in 4 and then I plug in 7. So I get 3.6 and 8.4. So it's 8.4 minus 3.6. So the average rate of change is whatever this is. What is it? 4.8 divided by 3, which is a 1.6. Done. That is the average rate of change between these 2 points for the given function. Careful. If I'm asked to, if these have measurement units, then the measurement unit for 1.6 will consist of 2 measurement units. One coming from the top / over, one coming from the denominator. So let's look at a word problem now.
Will the
Yes.
how to put a calculator again?
Say it again.
Can you show how to put it in a calculator again?
Yes. So we put in the function. You go to second and table set. There is a video. I recorded this. It's posted. Make sure that the independent variable is in the ask mode.